back to my Knowledge Hub, the channel where we delve into the depths of knowledge to bring you insights that can enhance your understanding of various topics. Today, we are diving into the world of hypothesis testing, a fundamental tool in statistical inference. Specifically, we'll be exploring the nuances of one-tailed and two-tailed hypothesis tests, the significance of these tests, and the critical concepts of type 1 and type 2 errors. So, let's jump right in. 1. One-tailed and two-tailed hypothesis tests. In the realm of hypothesis testing, researchers face a critical decision whether to use a one-tailed or two-tailed test. The choice depends on the nature of the research question and the hypothesis being tested. Let's break down these concepts. A one-tailed hypothesis test, also known as a directional test, comes into play when researchers have a specific expectation about the direction of the relationship or difference between variables. Take the example of testing a new drug's impact on blood pressure. The researcher might hypothesize that the drug reduces blood pressure. In this case, a one-tailed test is apt since the direction of the expected effect is explicitly stated. To conduct a one-tailed test, the researcher calculates a test statistic and compares it to the critical value. If the statistic falls into the critical region, determined by the chosen level of significance, the null hypothesis is rejected in favor of the alternative hypothesis. On the flip side, a two-tailed hypothesis test, also known as a non-directional test, is used when there is no specific expectation about the direction of the relationship or difference between variables. Continuing our drug example, if the researcher is interested in whether the drug affects blood pressure without specifying the direction, a two-tailed test is suitable. The critical region in a two-tailed test is divided equally between both tails of the distribution. If the test statistic falls into either tail, the null hypothesis is rejected. The choice between one-tailed and two-tailed tests hinges on the research question, the hypothesis, and practical considerations. One-tailed tests are more powerful when a specific direction is expected, but caution is needed as they should only be used with a strong theoretical or empirical basis. Two-tailed tests, providing flexibility for differences in either direction, are more suitable when there's no clear expectation. Now that we understand the fundamentals of hypothesis testing, let's explore the formal process statisticians follow to determine whether to reject a null hypothesis. 2. How to conduct hypothesis tests. Hypothesis testing involves 4 key steps. Step 1. State the hypotheses. The first step is to clearly state the null and alternative hypotheses, ensuring they are mutually exclusive. For instance, in our drug effectiveness example, the null hypothesis might state the drug has no effect, while the alternative hypothesis asserts the drug does have an effect. Step 2. Formulate an analysis plan. The analysis plan outlines how to use sample data to evaluate the null hypothesis. This includes specifying the significance level and the test method. Common significance levels are 0.01, 0.05, or 0.10, and the test method involves a test statistic and a sampling distribution. Step 3. Analyze sample data. In this step, the researcher computes the test statistic, considering the significance level and the critical region. The test statistic is compared to critical values, and if it falls into the critical region, the null hypothesis is rejected. Step 4. Interpret results. The final step involves applying the decision rule from the analysis plan. If the test statistic's probability is less than the significance level, the null hypothesis is rejected. Moving on to our next segment, let's explore the crucial concept of the test of significance. 3. Test of significance. The test of significance, also known as the hypothesis test, is a vital component of hypothesis testing. It allows researchers to determine whether observed results are statistically significant or merely due to chance. The test of significance helps assess the strength of evidence against the null hypothesis, representing the status quo or the absence of an effect. Conducting a test of significance involves several steps. Step 1. Formulate the null and alternative hypotheses. Clearly define the null and alternative hypotheses based on the research question. Step 2. Select the test statistic. Choose a test statistic based on the nature of the data and research question. Step 3. Determine the level of significance. Set the significance level, often denoted as alpha, indicating the maximum probability of making a type 1 error. Step 4. Calculate the test statistic. Using sample data, compute the test statistic representing the observed difference between the sample data and the null hypothesis. Step 5. Determine the critical region. Define the critical region based on the significance level and the distribution of the test statistic. Step 6. Compare the test statistic with the critical region. If the test statistic falls into the critical region, reject the null hypothesis, otherwise, do not reject it. Step 7. Draw conclusions. Conclusions are drawn based on whether the null hypothesis is rejected or not. Interpreting the test of significance. The test of significance provides a quantitative measure of the strength of evidence against the null hypothesis, often represented by the p-value. If the p-value is less than the chosen level of significance, the null hypothesis is rejected. However, rejecting the null hypothesis doesn't prove the alternative hypothesis to be true. Importance of test of significance. The test of significance is crucial in research and decision-making, offering an objective approach to hypothesis testing and ensuring the validity and reliability of findings. Now, let's delve into the intricacies of Type 1 and Type 2 errors in hypothesis testing. 4. Type 1 and Type 2 errors in hypothesis testing. In hypothesis testing, understanding the potential errors is paramount. Type 1 and Type 2 errors can impact the validity of conclusions. Type 1 error. Type 1 error, also known as a false positive, occurs when the null hypothesis is rejected even though it is true. For instance, if a researcher falsely concludes that a new drug is effective when it has no effect, that's a type I error. Type 2 error. On the other hand, Type 2 error, or a false negative, occurs when the null hypothesis is not rejected even though it is false. If a researcher fails to detect the effectiveness of a drug that does have an effect, that's a Type 2 error. Balancing Type I and Type 2 errors. There's a trade-off between Type I and Type 2 errors. Decreasing the level of significance reduces the chance of Type I errors but increases the chance of Type 2 errors, and vice versa. Researchers must carefully consider the consequences of each error type based on their research context. Decision rules. Decision rules guide the rejection or acceptance of the null hypothesis. This can be done either with reference to a p-value or a region of acceptance. The p-value measures the strength of evidence, and if it's less than the significance level, the null hypothesis is rejected. Alternatively, the region of acceptance defines a range where the null hypothesis is not rejected. Understanding Type I and Type 2 errors. In summary, understanding Type I and Type 2 errors is crucial in hypothesis testing. Researchers must strike a balance between the two based on the specific goals and requirements of their study. Moving forward, let's explore the role of the level of significance and confidence intervals in hypothesis testing. 5. Level of significance and confidence interval. In hypothesis testing, the level of significance is a critical factor in determining the strength of evidence against the null hypothesis. A lower level of significance reduces the chance of Type I errors but increases the chance of Type 2 errors, while a higher level does the opposite. Confidence intervals. Confidence intervals provide a range of plausible values for an unknown population parameter based on sample data. The confidence level represents the probability that the interval contains the true population parameter. Common confidence levels are 90%, 95%, and 99%. For example, if we construct a 95% confidence interval for the mean of a population, it means that approximately 95% of such intervals would contain the true population mean. Factors influencing confidence intervals. The width of a confidence interval depends on factors like sample size, data variability, and the chosen confidence level. A larger sample size leads to a narrower interval, providing more precise estimates. Importance of level of significance and confidence intervals. In practice, both the level of significance and confidence intervals are crucial for making informed decisions in research. The level of significance gauges the strength of evidence against the null hypothesis, while confidence intervals provide a range of plausible values for the population parameter. That wraps up today's deep dive into hypothesis testing, covering one-tailed and two-tailed tests, the test of significance, Type 1 and Type 2 errors, and the significance of the level of significance and confidence intervals. Remember, understanding these concepts is essential for making informed decisions in research. If you found this video helpful, don't forget to like, share, and subscribe to my Knowledge Hub for more insightful content. Until next time, keep exploring the vast world of knowledge.